So let's take a look at arc length and curvature. So let's say we have a vector function rt and it has its components f of t, g of t, and comma h of t. Now in order to take or find the arc length of this vector function, we must first derive r of t. So r prime of t will obviously be equal to f prime of t, comma g prime of t, comma h prime of t. And so now the formula for arc length is going to be equal to the integral from a to b, and now a to b are going to be in terms of t, of the square root of the x component of the derivative, so f prime of t squared, plus the y component squared, so g prime of t squared, plus the z component squared, so h prime of t squared dt. And so to put the formula in the most compact form, the arc length is going to be equal to the integral from a to b of the magnitude of r prime of t. So let's say for number 1 we have to find the length of the curve of r of t equals 2 sine t, 5t, and 2 cosine t, and we're going from the bounds of -10 to 10. So the formula once again for the arc length is going to be the integral from a to b of the magnitude of r prime of t. So notice we must find r prime of t first. So r prime of t, or the derivative of the vector function that is given to us, is going to be, well, the derivative of 2 sine t is going to be 2 cosine t. The derivative of 5t is going to be 5, and the derivative of 2 cosine t is -2 sine of t. So now remember, in order to find the magnitude of the derivative, we must take the square root of each component squared. So we have to take the square root. So the magnitude of r prime of t is going to be equal to the square root of the x component squared. So 2 cosine t squared is going to be 4 cosine squared t, plus the y component squared, so 5 squared will be 25, and then plus the z component squared, so -2 sine t squared would be 4 sine squared of t. Now if we were to simplify this, we can a little bit, but let's go ahead and group 4 sine squared and 4 cosine squared together and factor out a 4. So if I group them together, we'll get 4 cosine squared t plus 4 sine squared t plus 25, and then I can go ahead and factor out a 4. So we'll get the square root of 4 times cosine squared t plus sine squared t, and then plus 25. Now remember the trig identities, cosine squared plus sine squared is 1, so then 1 times 4 gives us 4, and then 4 plus 25 is 29. So we'll basically end up getting the square root of 29 as the magnitude of the derivative of the vector function. So now if I were to go ahead and rewrite the formula, the arc length is going to be equal to the integral from a to b. Now our bounds are from -10 to 10, so our a bound is going to be -10, our b is going to be 10, and then we have the magnitude of r prime of t, which we found to be the square root of 29 dt. So the integral of the square root of 29, since square root of 29, remember, is just a constant, so the integral is just square root of 29t, and then we're going to integrate from the bounds -10 to 10. So we'll get 10 times the square root of 29 minus a -10 times the square root of 29, so plus 10 times the square root of 29. And the final answer will be 20 times the square root of 29 as the arc length of the curve. So let's say for number 2 we have r of t equals square root of 2 times t I plus e to the tj plus e to the -tk, and we're integrating from the bounds of 0 to 1. So let's go ahead and find r prime of t first, so the derivative of our vector function. So r prime of t is going to be, well, the derivative of the square root of 2 times t is simply just the square root of 2 times I, because that's our x component, and then plus the derivative of e to the t is e to the t, so we have e to the t times j, our y component, and then plus the derivative of e to the -t, which is going to be negative e to the -t. So I can actually switch the plus to a minus and say minus e to the -t times our z component k. So now let's go ahead and find the magnitude of r prime of t. So in this case, the magnitude is going to be the square root of the x component squared. so that'll be 2, plus the y component squared, which is e to the t squared, and then plus the z component squared, e to the negative t squared. So when you have a power to a power, you can simply just multiply the powers. So I'm going to go ahead and simplify that. So we get the square root of 2 plus e to the 2t plus e to the negative 2t. So once again, the length is going to equal the integral from a to b of the magnitude of r prime of t dt. So if I were to rewrite the formula here, the length is going to equal to the integral. Now our bounds of integration are from 0 to 1. So our a bound is 0, b is 1. And then we have the magnitude of r prime of t, which we've found to be this value here. So the square root of 2 plus e to the 2t plus e to the negative 2t dt. Now you can always use a calculator to solve this problem since it's a definite integral, but in this problem I'll show you how to do it by hand. So for right now, it looks pretty much impossible to integrate this by hand, so what we need to do is adjust what's inside of the radical. So I'm going to start by factoring out e to the 2t. So if I do that, under the radical we get e to the 2t times, now if I factor out e to the 2t from 2, we'll get 2 over e to the 2t, and then plus 1, and then plus e to the negative 4t. Because if I multiply e to the 2t and e to the negative 4t, we'll get back to e to the negative 2t. So now remember that we can rewrite e to the 2t as e to the t squared, and since this is being multiplied, if we go ahead and take the square root of e to the t squared, they'll cancel and we're left with e to the t. So we can bring that outside of the radical. So I can rewrite it as e to the t times the square root of what's left inside, so 2 over e to the 2t plus 1 plus e to the negative 4t. So now what I'm going to do is just focus on what's inside of the radical. And then I'm going to go ahead and find a common denominator and add all these together to create one whole fraction. So let's go ahead and write out each individual fraction. So we have 2 over e to the 2t plus 1 plus, now I'm going to rewrite e to the negative 4t as 1 over e to the 4t. So now I'm going to make the common denominator e to the 4t and go ahead and add all the fractions. So I'm going to multiply 2 over e to the 2t, and we'll multiply that by e to the 2t over e to the 2t to get the denominator of e to the 4t. Now for 1 I can just rewrite as e to the 4t over e to the 4t to get the common denominator once again of e to the 4t, and then we already have the common denominator on the third term of 1 over e to the 4t. So when I go ahead and multiply these two, we'll get 2e to the 2t over e to the 2t times e to the 2t. When the bases are the same, we can just add the powers. So we get 4t. Now plus e to the 4t over e to the 4t, and then plus 1 over e to the 4t. So now we can go ahead and add the fractions together. So when I add the fractions, we'll get 2e to the 2t plus e to the 4t plus 1 over all over e to the 4t. So now what I'm going to do is go ahead and rearrange the top terms so that the highest power, so e to the 4t, comes first. And I'm going to rewrite it as e to the t to the 4th, because remember, when there's a power to a power, you can just multiply. So if we do that, we'll get back to e to the 4t. So we have e to the t to the 4th, plus the next term is going to be the second highest power. So we have 2 times, now I'm going to rewrite e to the 2t as e to the t squared, and then plus 1 over e to the 4t. So now realize this is in fact a perfect square trinomial, and we can rewrite it as e to the t squared plus 1 squared over e to the 4t. So now since we have turned this under the radical into this, I'm going to go ahead and replace that. So now when I go ahead and replace this with this, now that we have turned it into that, we can rewrite it as e to the t times the square root of the entire thing. So now I can rewrite e to the 4t once again as e to the t to the fourth. So we have e to the t all to the fourth power. And so this is pretty easy because when we take the square root of e to the t squared plus 1 squared, they'll cancel. And so we're left with e to the t squared plus 1 on the numerator. And then the square root of e to the t to the fourth is simply e to the t squared. And then we also have that e to the t up front. So when I rewrite it, we'll get e to the t times e to the t squared plus 1 over e to the t squared. So now we can go ahead and divide these two terms. So e to the t divided by e to the t squared, we go ahead and subtract the powers. So we'll get e to the t to the negative first, or just 1 over e to the t. So we can rewrite it as e to the t squared plus 1 over e to the t. So now what I can do is separate into two different fractions. So we have e to the t squared over e to the t plus 1 over e to the t. So e to the t squared divided by e to the t is just e to the t to the first, or e to the t. And then we have plus 1 over e to the t, which is e to the negative t. So now, given that we transform this entire radical into e to the t plus e to the negative t, we can go ahead and rewrite the integral as the integral from 0 to 1 of e to the t plus e to the negative t dt. So now the integral of e to the t is obviously just e to the t. And then the integral of e to the negative t, now we could use u substitution, but really the integral of e to the negative t is just negative e to the negative t. So we have plus negative e to the negative t. Or I can just remove the plus and put it as minus. So now we have e to the t minus e to the negative t. And we're going to evaluate from 0 to 1. So if I go ahead and plug in 1, we'll get e to the first, which is just e, minus e to the negative first. And then minus, when I plug in 0, so e to the 0 is 1, and then minus e to the negative 0 is still going to be 1. 1 minus 1 is 0, and that will cancel. And so our final answer is going to be e minus e to the negative first, or you can also rewrite it as e minus 1 over e. And that's the final answer. So let's go ahead and find the length of the vector function r of t equals I plus t squared j plus t cubed k, and we're going from t values of 0 to 1. So let's go ahead and find r prime of t first. So r prime of t equals, now the derivative, the coefficient in front of I is just 1. So if the x component is 1, derivative 1 is 0. And so that will cancel out the I, make it 0i. Now plus the derivative of t squared is simply just 2t, so 2tj. And then plus the derivative of t cubed is 3t squared k. And so 0i will cancel, obviously, because that's 0. And so if we rewrite the integral here, or the integral for the arc length, we get the integral now from a to b, so from 0 to 1, of the magnitude of r prime of t dt. So now in order to find the magnitude of r prime, let's go ahead and take the square root of the x component squared. The x component squared is 0, so 0 squared is 0, plus the y component squared, which is 4t squared, plus the z component squared, which is 9t to the fourth. So rewriting the integral, we get the integral from 0 to 1 of the magnitude of r prime, which we've found to be the square root of 4t squared plus 9t to the fourth dt. So now the very first thing I would do is go ahead and focus on what's inside of the radical and go ahead and factor out a t squared. So just focusing on what's inside the radical, we get t squared times 4 plus 9t squared. Now, since these are being multiplied here, the square root of t squared is simply just t, so we can bring that outside of the radical. So we get t times the square root of 4 plus 9t squared. So now if I rewrite the integral from 0 to 1 of t times the square root of 4 plus 9t squared, this is just a simple u substitution problem. Let's go ahead and make u equal to 4 plus 9t squared, which means du, or the derivative, will equal 18t dt. So then if we isolate dt, dt is going to equal du over 18t. So if I go ahead and substitute that in for dt and substitute 4 plus 9t squared with u, we'll get the integral from 0 to 1 of t times the square root of u times dt, which is equal to du over 18t. So notice that t's will cancel. 1 over 18 can come out as a constant, so we get 1 over 18 times the integral of the square root of u, or u to the 1/2 du. So the integral of u to the 1/2 would be u to the 3/2 divided by 3/2 or multiplied by 2/3. So 2 divided by 18 can be simplified into 1 over 9, and 1 over 9 times 1 over 3 is 1 over 27. So we get 1 over 27 u to the 1/2, or sorry, u to the 3/2. Remember, u we set to be 4 plus 9t squared. So we get 4 plus 9t squared, the entire thing to the 3/2 power, over 27. Now I apologize, I forgot to put the bounds here. So remember we are integrating from 0 to 1. So we're going to go from 0 to 1 as our bounds. And so when I go ahead and plug in 1, we'll get 9 times 1 squared, which is 9, plus 4, 13. So we'll get 13 to the 3/2 power over 27. And then minus when I plug in 0, we'll get 4 to the 3/2, which is 8. So 8 over 27. So we can rewrite it as 13 to the 3/2 minus 8 all over 27. And that is an acceptable final answer. So now the next set of problems are going to be about curvature. And so curvature is how fast a curve can change direction at a given point. So curvature symbol is just a lowercase k, or the Greek letter lowercase kappa. And so the formula for that, now there are many formulas for curvature, but the most convenient one to use is going to be the magnitude of the cross product of r prime of t and r double prime of t. So the first derivative and the second derivative, the cross product of both, over the magnitude of r prime of t, and we're going to take that to the third power. Now in special cases where the equation given to you is y in terms of f of x, then you can use a different formula for the curvature, and that is going to be equal to, now it's going to be curvature in terms of x. The other one is in terms of t, notice that. And so that is going to be equal to the magnitude, or the absolute value, of f double prime of x over, now we're going to take 1 plus f prime of x, and now f prime of x is going to be squared, and then we're going to take the entire denominator to the 3/2 power. And so that is going to be the formula for the curvature when given a function in terms of f of x. So for number 1, let's go ahead and find the curvature for the function r of t equals t squared I plus t times k. So the formula once again for curvature is going to be equal to the magnitude of r prime of t times, now we're taking the cross product of r prime of t and r double prime of t, over the magnitude of r prime of t to the third power. So let's go ahead and first find r prime of t and the second derivative r double prime. So r prime of t is going to be equal to, now the x component is going to be t squared since that's with the I. So the derivative of t squared is just 2ti. Notice there is no j vector associated with the y component, and so since that is 0, the derivative of 0 is still going to be 0, so we don't worry about the y component. And then we have plus t times k. So the derivative of t is 1, so 1 times k will just give us k. So now if we were to write that in component form, we could write it as the x component, which is 2t, the y component is 0, and the z component is 1. Now our double prime of t, the second derivative, we're going to take the derivative of 2t, which is just 2, so we have 2i. The j, or the y component, is still 0, and then we have plus the derivative of 1 times k. So the derivative of 1 is 0, so 0 times k would still be 0. So we're just left with 2i. And so in component form, that would be 2, which is associated with the x component, 0 for y, and 0 for the z component. So now let's go ahead and take the cross product of r prime and r double prime. So the cross product of r prime and r double prime is going to be equal to, now we need to make a matrix here of ij and k on the top. Since r prime is being multiplied first, we'll put its component first. So we have 2t, 0, and 1. And then for r double prime, we have 2, 0, and 0. So now we need to find the determinant here. we're going to take the first top left value, I, multiplied by, if we cross out its row and column, we're left with 0, 1, and 0, 0. The second term is going to be minus, or negative here. So j, if we cross out its row and column, we're left with 2t1 and 2, 0. And then the third term is going to be a positive, so we have plus k times, if we cross out its row and column, we're left with 2t times 0, and or 2t and 0, and 2 and 0. So now let's go ahead and cross multiply. So we get I times 0, which is 0, minus 0 times 1, which is 0, minus j times 2t times 0 is 0, minus 2 times 1, which will give us 2, and then plus k times 2t times 0 is 0, minus 2 times 0 will also give us 0. So obviously these will cancel, and so we're left with negative j times negative 2. So that will give us 2j as the cross product vector. Now if we were to write 2j in its component form, we could also write it as, now the j goes with the y component. So the x component is 0, our y component is 2, and the k or the z component is still 0. And so we need to find the magnitude of the cross product. So since we found the cross product already, let's go ahead and find the magnitude of this. So that's just going to be the square root of the x component squared plus the y component squared plus the z component squared. And so we'll get the square root of 4, or 2. So now we need to take that over the magnitude of the derivative cubed. So let's go ahead and find the magnitude of r prime. So the magnitude of r prime of t is going to be equal to the square root of, once again, the x component squared, so 2t squared is going to be 4t squared, plus the y component squared, plus the z component squared. And so we're left with the square root of 4t squared plus 1. And so we need to take that magnitude to the third power. So if I take this to the third power, now we can rewrite this as 4t squared plus 1 to the 1/2. So 1/2 to the third is to the 3/2. So we can rewrite it as 4t squared plus 1 all to the 3/2 power. And so we have found the magnitude of the cross product of r prime and r double prime of t to be equal to 2. And we have found the magnitude of r prime of t cubed to be equal to 4t squared plus 1 to the 3/2. So this is going to be the equation for the curvature at any given point t. So now for number 2, let's go ahead and find the curvature for y equals 4x to the 5/2. So notice we are in the form y equals some function in terms of x, so we can use the special formula for curvature, where the curvature is going to equal the magnitude of f double prime of x over 1 plus f prime of x squared, and the entire thing to the 3/2 power. So let's go ahead and find f prime and f double prime. So if y equals 4x to the 5/2, f prime or y prime is going to equal 4 times 5/2, so 20 over 2, which is 10, x to the 5/2 minus 1, so 3/2, and then y double prime is going to equal 10 times 3/2, so 15, x to the 1/2. So now rewriting the curvature formula here, we get the magnitude or the absolute value of f double prime, so 15, I'm going to rewrite it as the square root of x, over, now 1 plus, now f double or f prime of x squared. So if f prime is 10x to the 3/2, if we take 10x to the 3/2 squared, we'll get 100x to the 6/2, or 100x to the third power. So 100x cubed, now the entire thing to the 3/2. And so if we look at the graph of the square root of x, notice square root of x is always going to be above the x-axis, so it's always going to be positive. So we can go ahead and drop those absolute value signs. So the final answer is going to be 15 times the square root of x over 1 plus 100x cubed all to the 3/2 power. So remember, this will give you the curvature at any given point x. So now the next set of questions are going to be about unit tangent vectors, unit normal vectors, and binormal vectors. So remember that the unit tangent vector, written as capital T of t, is going to be equal to r prime of t over the magnitude of r prime of t. So remember, the tangent vector is going to be tangent to a curve at a given point t. Now a normal vector is going to be written as n of t, capital N of t, and since tangent is tangent, normal is going to be the opposite of tangent, or perpendicular. So the normal vector is going to be perpendicular to the curve at a given point t. And so the formula for a normal vector is going to be the derivative of the unit tangent vector over the magnitude of the derivative of the unit tangent vector. And so now a binormal vector is written as b of t, capital B of t. And if tangent is tangent, normal is perpendicular, binormal is going to be the cross product of the tangent vector, or the unit tangent vector, and the unit normal vector. So the binormal vector is going to be perpendicular to both the tangent and the normal one. Since we take the cross product, and the cross product we know yields a vector that is tangent or perpendicular to both the cross products, vectors that we multiply. So let's go ahead and find the unit tangent, unit normal, and binormal vectors for the first problem we did in this video. The function, vector function r of t is going to be equal to 2 sine t, 5t, and 2 cosine t. So starting off with finding the unit tangent vector, obviously that is going to be equal to r prime of t over the magnitude of r prime of t. So let's go ahead and find r prime of t. So r prime of t is going to be equal to the derivative. So the derivative of 2 sine t is going to be 2 cosine t. The derivative of 5t is going to be 5. And the derivative of 2 cosine t is negative 2 sine of t once again. And so the magnitude of r prime is going to be the square root of the x component squared. So 2 cosine t squared is 4 cosine squared of t plus 25 plus 4 sine squared of t. So similar to earlier in the video, we combined 4 cosine, 4 sine squared. So we got 4 times 1, which is 4, and then 4 plus 25 gives us the square root of 29. And so the unit tangent vector here is going to be equal to r prime of t, which we found to be 2 cosine t, comma 5, comma negative 2 sine of t, all over the magnitude of r prime, which we found to be the square root of 29. So I can rewrite it as taking every single component and dividing it by the multiple square root of 29. So we get 2 over square root of 29 cosine t, comma 5 over square root of 29, comma negative 2 over square root of 29 sine of t. So that is going to be the unit tangent vector. Now the unit normal vector, so capital N of t, is going to be equal to the derivative of the unit tangent vector over the magnitude of the derivative of the unit tangent vector in terms of t. So now let's go ahead and find the derivative of the unit tangent vector. So t prime is going to be equal to, in component form, well, the derivative of 2 over the square root of 29 cosine t is going to be negative 2 over the square root of 29 sine of t, comma, the derivative of a constant is simply just going to be 0, and then we have the derivative of negative 2 over the square root of 29 sine of t, which is negative 2 over the square root of 9 cosine t. Now the magnitude of t prime of t, or the magnitude of the unit tangent vector, is going to be equal to the square root of the x component squared. So if we take this squared, we're going to get positive 4 over 29 sine squared of t. And we have plus the y component squared, that's just simply going to be 0, so we'll leave that out. Plus the z component squared, and so that would also give us 4 over 29 times cosine squared of t. Now we go ahead and say factor out 4 over 29, so we get sine squared plus cosine squared, which is 1. So we basically get 4 over 29 inside the radical. So we get the square root of 4 over 29. So that would be the square root of 4 over the square root of 29. Square root of 4 is 2, and then we get the square root of 29 at the bottom. So that means that the normal vector, n of t, the unit normal, is going to be the derivative of the unit tangent, which we found to be this. So we have the square, or the negative 2 over the square root of 29 sine of t, comma 0, comma negative 2 over square root of 29 cosine t. And then we can take that all over the magnitude of the unit tangent vector, or the magnitude of the derivative of the unit tangent vector, which we have found to be 2 over the square root of 29. So now I can go ahead and divide each component by the multiple 2 over square root of 29. So n of t, or the unit normal vector, is going to be equal to, now if I take negative 2 over square root of 29 and divide it by 2 over square root of 29, I'm basically multiplying. So if I have negative 2 over square root of 29, I'm multiplying by the reciprocal. So then the 2's will cancel, the 29, so square root of 29's will cancel, and so we're left with a negative 1. So the x component is going to be negative sine of t. Now the y component remains 0. And the z component is the same thing. We're left with negative 1 times cosine t. So this is going to be the unit normal vector. So now in order to find the binormal vector, remember the binormal vector is going to be the vector that is perpendicular to both the unit tangent and the unit normal. So in order to find that, we must take the cross product of the unit tangent vector and the unit normal vector. So to take the cross product here, so we take t, or the unit tangent vector, times the unit normal vector. So that's going to equal, now we need to go ahead and create a matrix. We need to have I, j, and k here. And so since unit tangent is being multiplied first, let's go ahead and put its components down on the second row. So we have 2 over the square root of 29 cosine t. We have 5 over the square root of 29. And then for our k or z component, we have negative 2 over square root of 29 sine of t. Now for the components of the normal vector, the unit normal, we have negative sine of t, 0, and negative cosine t. So now let's go ahead and find the determinant of this matrix. So once again, we're going to take the first top left term, so I, times, now we cross out the row and column i's in, and we write what's left inside. So we have 5 over the square root of 29. We have negative 2 over the square root of 29 sine of t. And then we have 0 and negative cosine t. Now the second term is going to be a negative, so we have j times, now the matrix of, now we can cross out the row and column j's in. So we're left with 2 over square root of 29 cosine t, negative 2 over square root of 29 sine of t, negative sine of t, and negative cosine t. And then the k, the third term, is going to be positive. We cross out the row and column k is in, and we're left with, inside the matrix, 2 over square root of 29 cosine t, 5 over square root of 29, and then negative sine of t, and 0. So now let's go ahead and cross multiply. So we get I times, now 5 times the square root of 20, or 5 over the square root of 29, times negative cosine t, so I'll put negative 5 and cosine t. Now minus, when we multiply 0 times negative 2 over square root of 29 sine of t, we get 0. Minus j times, now we take the cross multiplication of these two, so we have negative 2 over square root of 29 cosine squared of t. Now minus, when we cross multiply these two, we get 2 over square root of 29 sine squared of t. And then we have plus k times, now 0 times that term would be 0, then minus a negative, so we have positive here, 5 over square root of 29 sine of t. So we're left with I times negative 5 over square root of 29 cosine t minus j times negative 2 over square root of 29. Now if I go ahead and, I can go ahead and factor out a negative 2 over square root of 29 from both terms here. So we get negative 2 over square root of 29 times, now cosine squared of t, and then plus sine squared of t, and then plus k times 5 over square root of 29 sine of t. So our final answer for the binormal vector, the vector that is perpendicular to both the unit tangent and the unit normal vector, is going to be equal to, now we have negative 5 over square root of 29 cosine t times I, the x component. Now cosine squared plus sine squared is 1, so we can cancel that, and 1 times negative 2 over the square root of 29 is still the same. And so notice the negatives will cancel, so we'll get a positive 2 over the square root of 29 times j, the y component, and then we have plus right here 5 over the square root of 29 sine of t times the unit vector k. And so that is going to be the final answer for the binormal vector. So realize that this vector is going to be perpendicular to both unit tangent and the unit normal.